Hi everyone, welcome back to Made Everything Official. Molten metal is poured into hand-packed sand molds at Billets foundry, where traditional casting methods shape each component by hand. The process begins with mold preparation, as sand is compacted around a pattern to form the cavity of the final part. Proper compaction is critical, since mold stability directly affects surface quality. Metal is melted in the furnace and brought to pouring temperature before being guided into the mold. A controlled pour allows the metal to flow evenly, reducing turbulence and preventing defects during solidification. Once cooled, the sand mold is broken apart to release the raw casting. Excess sand and material from gates and runners are removed. The casting then enters finishing operations, where cutting and grinding refine edges and remove unwanted sections. Manual dressing completes the process, producing a finished casting ready for use. Inside this factory in Jamnagar, short solid metal billets are transformed into a wide range of brass rods and hollow sections through a fully integrated manufacturing process. What begins as compact, round metal blocks is gradually reshaped using heat, pressure, and precise tooling to create tubes and profiles with consistent geometry. This production line demonstrates how controlled extrusion and downstream processing convert raw alloy into engineered brass products ready for industrial use. The process starts with raw brass and alloy billets being inspected and prepared for production. These solid blocks are fed into heating furnaces where the metal is brought to controlled temperatures needed for shaping and extrusion. Maintaining the correct temperature ensures the metal becomes pliable without compromising material properties. Once heated, the billets enter the extrusion press. Powerful hydraulic force pushes the soft metal through a die, forming long continuous rods or hollow sections in the desired profile. The shape of the die determines the cross-sectional form, whether round rods, hollow tubes, or special profiles. As the extruded material exits the press, it is guided through cooling beds to solidify uniformly. Controlled cooling is essential to prevent warping and to maintain consistent dimensions along the entire length of the rod or hollow. Following cooling, the rods are straightened and cut to the specified lengths. Precision cutting equipment ensures each piece meets dimensional requirements, and operators monitor alignment and surface quality to reduce defects. Next, the cut sections pass through finishing operations. Surface grinding and polishing remove scale or surface marks left from extrusion and cooling, giving the final product a smooth, machinable finish. Hollow sections may receive additional processing to refine internal surfaces and ensure bore consistency. Throughout the line, quality checks are performed at key stages, including dimensional inspection and surface evaluation, to guarantee that each rod and tube conforms to engineering standards. Completed brass rods and hollow tubes are then bundled and prepared for shipment to customers in various sectors such as automotive, electrical, plumbing, and industrial applications. From the customer's initial idea to the finished component, this process illustrates how aluminum gravity casting is carried out within the ALU network production workflow. The sequence begins with solid aluminum ingots being loaded into the melting furnace. Inside the furnace, the metal is gradually heated and held at a controlled temperature until it reaches a stable molten state. Precise temperature control at this stage is critical, as it determines the fluidity of the aluminum and directly influences casting quality. Once the aluminum is fully molten, the melt undergoes an additional refining step. A small refining agent is introduced into the liquid metal and mechanically stirred. This treatment causes impurities and dissolved gases to rise to the surface as slag. Operators then carefully skim this layer away, cleaning the melt before casting. This step is essential for improving internal structure, reducing porosity, and ensuring consistent mechanical properties in the final parts. After refining, automated handling systems take over. Mechanical ladles collect the purified molten aluminum and pour it into permanent shell molds prepared for gravity casting. Unlike high-pressure processes, gravity casting relies on the natural flow of the metal to fill the mold cavity. Controlled pouring speed and alignment allow the aluminum to flow smoothly, minimizing turbulence and producing clean, well-defined shapes. The filled molds are left to cool under controlled conditions. Cooling time is carefully managed to ensure dimensional stability and to avoid internal stresses. Once solidification is complete, machines open the molds and extract the raw castings, which still include runners, gates, and surface imperfections formed during the pour. The castings then move into finishing operations. Initial manual grinding removes excess material, separates the casting from the gating system, and smooths rough edges. Hand finishing allows operators to visually inspect each part and refine complex shapes that require precise control and experience. For components requiring tighter tolerances or repeatable geometry, CNC machining is used to finish critical surfaces, holes, and reference features. Throughout the process, surface treatments and inspections prepare the parts for their final application. By integrating melting, gravity casting, manual finishing, and CNC machining, ALU Network delivers a complete manufacturing path that transforms raw aluminum into finished components ready for use. Stainless steel production at RIM-JHIM Steel begins with scrap material being prepared for melting. Incoming scrap is carefully charged into the furnace, where high temperatures transform it into molten stainless steel. Precise heat control at this stage is essential, as it directly affects strength, durability, and corrosion resistance. Once molten, the steel is refined inside the furnace. Chemical composition is adjusted and impurities are removed to achieve the required stainless steel grade. Continuous monitoring ensures the melt meets quality standards before further processing. The refined steel is then cast into semi-finished forms such as billets or slabs. These solid sections provide a controlled base for downstream shaping. Cooling conditions are managed to maintain internal structure and reduce defects. After casting, the material moves through rolling operations, where heavy-duty mills shape the steel into long and flat products. High pressure and temperature allow the steel to be formed evenly while preserving mechanical properties. Throughout the process, quality checks are performed at key stages. Dimensional accuracy and surface condition are inspected to ensure consistency. By combining modern equipment with strict process control, recycled scrap is converted into high-quality stainless steel ready for industrial use. At BGH, large-scale steel production operates alongside strict safety procedures designed to protect everyone inside the plant. The process begins with steelmaking and forging operations that involve extremely high temperatures. Furnaces, ladles, and casting areas radiate intense heat, so controlled pathways and clear safety zones are essential. Personnel working near these areas rely on protective equipment to reduce the risk of burns and heat exposure. Forging operations shape massive steel blocks while the material is still hot. At this stage, temperature control is critical, since improper handling can damage both the material structure and the equipment. After forging, components may be transferred into quenching systems, where special cooling liquids harden and stabilize the alloy. These tanks contain hot and reactive fluids, making direct contact extremely dangerous. Further processing takes place in machining areas. Drilling, grinding, cutting, and straightening operations refine forged steel into precise forms. During machining, sharp and often hot metal chips are produced, and rotating tools operate at high speed. Machine guards and safety enclosures are used to prevent accidental contact. Throughout the facility, automated transport systems move steel through storage and logistics areas. These zones are largely unmanned, as fully automated cranes and handling systems relocate heavy materials with precision. Outside the buildings, forklifts, trucks, and other vehicles circulate continuously, requiring strict adherence to marked routes. By combining advanced steel processing with comprehensive safety rules, BGH ensures that complex operations, from forging and heat treatment to machining and logistics, are carried out efficiently while minimizing risk across the entire production environment. Italian cookware, produced by Raffoni, begins its journey as high-quality copper blanks sourced for purity and conductivity. Before production begins, incoming copper blanks are inspected for surface finish and composition to ensure they meet stringent quality standards. The first major step in the manufacturing process is forming. The flat copper discs are placed into hydraulic presses or spinning lathes, where they are shaped into the basic form of pots, pans, or kettles. Skilled operators monitor the forming process, adjusting pressure and feed rates to achieve consistent wall thickness and smooth contours. Precision control at this stage is vital, as uneven walls can affect both performance and durability. CNC or manual lathes trim excess material and refine the profiles of rims and spouts. Surfaces are buffed and polished to a smooth finish, while interior cooking surfaces may receive additional brushing or coating to prepare them for performance testing. Once the basic shape is achieved, the cookware moves into annealing ovens. Controlled heating softens the copper, making it more ductile for further shaping, joining, and detailing. Annealing cycles are closely monitored to avoid overheating, which can lead to grain growth and weaken the metal. After annealing, parts are allowed to cool in a controlled manner to reduce residual stress. Next, some components undergo assembly and joining. Handles, rims, and decorative bands are fitted to the main body using mechanical methods such as riveting or soldering with high-temperature alloys. These joints must be secure yet seamless, contributing both to the cookware's structural strength and its aesthetic appeal. During this stage, craftsmen often check alignment, fit, and surface quality by eye and touch. Finally, every finished piece undergoes rigorous inspection. Once approved, pieces are cleaned, packed carefully, and prepared for shipment to chefs, restaurants, and retailers around the world. This video presents a sequence of specialized machines used to manufacture ammunition components through a controlled, step-by-step mechanical process. Production begins at the shotgun shell loading machine, where empty shells are positioned and filled with measured components to form a consistent base structure. The primer inserting machine follows, pressing primers into each case with controlled force. Shot production takes place at the shot casting machine, where molten lead is formed into small pellets. Controlled cooling produces uniform shot size, which is important for predictable ballistic performance. Lead wire is produced at the lead wire extrusion machine by forcing softened lead through dies. This continuous wire becomes the raw material for bullet cores. For heavier applications, the buckshot machine forms larger spherical pellets from molten lead. The lead core press then cuts and compresses the extruded lead wire into precise core shapes. Consistent weight and density are maintained to ensure uniform bullet performance. These cores move to the bullet jacketing machine, where metal jackets are applied around the lead core. Jacketing improves structural strength and controls deformation during firing. Further shaping occurs in the double action press, which refines bullet geometry through multiple forming steps in a single cycle. This ensures a consistent external profile. The resize machine calibrates each bullet to its final diameter, guaranteeing compatibility with firearm chambers. Trimming machines then remove excess material to set exact length, while grooving machines form channels that reduce friction and improve stability. Together, these machines create a continuous production flow that transforms raw materials into precisely formed ammunition components. Precision-cut circular blanks are produced in this automated machining service, where specialized cutting systems turn flat metal stock into accurate discs and rings. The process starts with raw plate or sheet being loaded and positioned on the table. Alignment stops and sensors verify the workpiece location, because even a small offset will throw off roundness and final diameter. Once referenced, the CNC program drives the cutting head along a perfect circular path. Feed rate and cutting pressure are tuned to the material thickness so the edge stays clean without warping the plate. Coolant or airflow clears chips and reduces heat buildup, protecting both the tool and the surface finish. As the cut completes, the circle is separated and removed, while the remaining skeleton is cleared for the next cycle. A quick dimensional check confirms diameter and edge quality, catching burrs or taper before parts move downstream.